The title of my presentation is Newton and Feynman on the Motion of the Planets Around the Sun. The two heroes of our story are Isaac Newton and Richard Feynman. Now, all Newton did was invent calculus, formulate his three famous laws of motion, and discover his universal law of gravitation. Along the way, he wrote one of the greatest scientific masterpieces of all time. He gave it a Latin title, and it's simply called the Principia for short. All of this work represented a revolution in understanding the motion of the planets around the sun. But what about this other guy? Here is Richard Feynman, another genius, who happened to live 300 years later. He won a Nobel Prize for his work in quantum mechanics, and he invented his famous Feynman diagrams, which nicely demonstrate his ability to find simple and elegant approaches to very complex and difficult problems. So why did he care about the Newtonian mechanics of planetary motion? That was old news. Einstein's theory of general relativity had already been proven to be an improvement on Newton's work. The answer to this question and many more can be found in a wonderful book entitled Feynman's Lost Lecture, The Motion of the Planets Around the Sun, by David L. Goodstein and Judith R. Goodstein. In fact, my presentation is based on Feynman's Lost Lecture as it was reconstructed in this book. For starters, I want you to imagine that it is 1964 and you are a freshman at Caltech, one of the leading science and engineering colleges in the country. You are taking the mandatory freshman introductory course in physics, and of course you love physics. Today, the great Richard Feynman, one of your heroes, has agreed to give a special guest lecture. Your heart is beating a little faster than normal, but you are a bit puzzled by Feynman's choice of topic, which seems a little boring. But then Feynman begins to speak.
You know that Newton invented the calculus, and you know that you can use calculus with some difficulty to work out the orbits of the planets. What you may not know, however, is that in the Principia, Newton's reasoning on this subject is based mostly on plane geometry. I am going to share some of that reasoning with you today. However, when I read the Principia, I always get to a point where I have a hard time following Newton's thought process. So, I cooked up some of my own explanations instead, also based on plane geometry. And that's what I want to tell you about today.
Before we go further, I want to remind you of where things stood at the time when Newton arrived on the scene. The three giants of early modern astronomy, Copernicus, Tycho Brahe, and Johannes Kepler, all assumed that the orbits of the planets to be circles, as circles were felt to have a mystical perfection appropriate to the heavenly realm of the stars and the planets. However, Brahe's extensive data for the motion of Mars did not quite fit this model. In particular, there was the Martian problem, the fact that at certain times Mars appeared to temporarily reverse direction in its path across the night sky. As Kepler's mentor, Brahe assigned him the task of figuring out the orbit of Mars. After first discovering what later became his second law, that the planets sweep out equal areas in equal times, he attacked the Martian problem with tenacious energy. He first assumed an ovoid, egg-shaped orbit, an assumption we will make later in part 3 of this talk. After 40 failed attempts, he gave up on the ovoid model. After earlier assuming that an ellipse was too simple a solution to have been ignored by his predecessors, he found, after all, that the Mars data fit
with an elliptical orbit. He immediately became convinced that all planets move in ellipses, with the Sun at one focus. We are now just about ready to appreciate how Newton, standing, as he said, on the shoulders of giants, explained the secrets of the heavens which Kepler discovered. But first,
let's start with Kepler's laws. Number 1, a planet's orbit is an ellipse. 2, a planet sweeps out equal areas in equal times. And 3, if t is the orbital period and r is the distance to the Sun, then t squared is proportional to r cubed. Now Kepler's laws are all based on very, very careful observations. They don't pretend to be fundamental laws of nature, but rather simply observational laws. Then we have Newton's laws. First, the law of inertia, which states that a body at rest will remain at rest unless a force acts upon it. And it also means that if a body is in motion, it will maintain its same velocity, that is, its same direction and speed, unless a force acts upon it. The second part of this law was not so intuitive. Aristotle, for example, believed that in order to keep a body in motion, one had to continuously apply force, because he did not realize that friction is almost always at play with motion on Earth. But friction does not necessarily exist in the solar system. Secondly, force equals mass times acceleration. 3, well, we don't need number 3 today, but you'll remember that it states that for every action there is an equal and opposite reaction. And finally, we need Newton's law of gravitation. It's called an inverse square law, and it states that the force of gravity, due to the Sun in this case, is inversely proportional to the square of the distance between the planet and the Sun. Now, unlike Kepler's laws, Newton's laws are proposed to be fundamental laws of nature that apply to all systems, not just our solar system. They are therefore intended to be, among other things, the theoretical basis for Kepler's observations. We want to find out if these two sets of laws are consistent with each other. Our strategy will be to show that Newton's first two laws, and nothing else, predict that a planet sweeps out equal areas in equal times. Then we will show that Kepler's second and third laws are consistent with an inverse square law for gravity. Finally, we will take all of the above and a few clever insights from Feynman and show that they establish that any planet's orbit is an ellipse. Let's start off really easy. Here is an imaginary planet, which we will call planet Q. Imagine that there are no forces acting on planet Q. Let's say it has an initial velocity of v sub a. Question: how far will planet Q travel in delta t if delta t equals 1 second and its velocity equals x meters per second? The answer, of course, is x meters. The displacement vector AB prime has a magnitude of x meters and is in the same direction as the velocity vector v sub a. We use b prime because we have not factored in gravity yet. As a formal equation, we write v sub a times delta t equals ab prime. Notice that the velocity v sub a does not change. Finally, I just want to add a few notes on notation. Displacement vectors will be in blue, velocity vectors will be in black, and force vectors will be in red. So that I don't have to add in little arrows every time, I'm going to use a new notation for vectors. Vectors will be indicated by curlicue brackets. If I just want to indicate the magnitude of a vector, I will use straight brackets, or if it's obvious, I won't use any brackets at all. Now let's add in the sun. It creates a gravitational force. We do not know the magnitude of the force vector at this point, but that does not matter for now. To keep things simple, Newton decides to turn on gravity for just a fraction of a second and then turn it back off. Let's call this fraction of a second delta t star and make it much, much smaller than delta t. Assuming the force to be constant over a short time interval, acceleration equals delta v divided by delta t star. And as I said, delta t star is a very, very small interval of time. As Newton himself put it in his notebooks, let the planet be attracted towards the sun by one impulse or impression of force. As you recall, an impulse has a specific and formal definition in physics nowadays. It equals force times delta t, or in this case, delta t star, and it equals a change in momentum. Since the mass is constant, the change in momentum directly translates into a change in velocity, delta v. So let's draw in delta v sub a. And we can get rid of the force vector. So now we have two velocity vectors for planet Q, and we want to add them to find the resultant velocity. How do we do that? We simply put the tail of one vector right on the head of the other vector. We get the resultant, which we call v sub b. Now we let the clock run forward 1 second, and we arrive at point B. And now the displacement vector, AB, equals v sub b times delta t. After one more second, we arrive at C prime. Again, we call this new point C prime to remind us that we haven't factored in gravity again, except for that initial impulse. Note that the displacement vectors AB and BC prime are equal, both being equal to v sub b times delta t. Before we introduce a gravity effect again, let's pause and look at two triangles, SBC prime and SBA. Question: does planet Q sweep out equal areas in equal times? In other words, are the areas of these two triangles equal? To find out, let's first draw in the altitudes, which I have done here, AM and C prime N. First, we can show that triangles 1 and 2 are congruent. Remember, AB and BC prime are equal, both being equal to v sub b times delta t. They are both right triangles, and these angles indicated here in magenta are equal because the opposite angles of two intersecting lines are always equal. So the two triangles pass the angle-angle side test for congruence. Back to the earlier question, are the areas of triangles SBC' and SBA equal? We have shown that the altitudes are the same. Let's call them H. Notice that they share the same base, SB, which we call B. The areas of SBC' and SBA are therefore equal because both are equal to 1/2 times B times H. So, planet Q with gravity turned off is sweeping out equal areas in equal times. Let's go back 1 second in time and turn gravity on for delta T star when planet Q is at B. And let's replace the force vector with a delta velocity vector like we did before. We call it delta V sub B. As before, we add the two vectors. This time V sub B plus delta V sub B equals V sub C. And after 1 second, we arrive at point C. Now we have a third triangle, SBC. First, we want to ask, are the areas of triangle SBC' and SBC equal? Well, recall that C'C is parallel to delta VB, which is parallel to the force of gravity, which is directed towards the sun along the path SB. So C'C and SB are parallel. And when we draw in the altitudes, CO and C'P, they are both equal because they each represent the distance between two parallel lines, which is constant. Again, we call these altitudes H, and once again, the two triangles share the base, SB. So the area of SBC' and the area of SBC are equal because they both equal 1/2 times base times height. We have shown that the area of SBA equals the area of SBC' and the area of SBC' equals the area of SBC. Therefore, the area of SBA equals the area of SBC. And once again, we see that the planet is sweeping out equal areas in equal times. We could repeat this process indefinitely in leapfrog fashion and go all the way around the orbit. This, in fact, is what Newton had in mind. And here is an actual drawing from Newton's notebook. And you can clearly see that he was going through the same thought process that we just did. These three famous English scientists were contemporaries, and they liked to get together sometimes to exchange ideas. Edmund Halley was an astronomer and of course was famous for the discovery of Halley's Comet. Hooke was a very smart scientist and is famous for some of the earliest discoveries with the microscope. Anyway, one night Halley and Hooke are having a pint of ale in a London pub, and Hooke mentions this idea going around that the sun exerts a force on a planet that is proportional to the inverse of the square of the distance between them. Halley nods his head, and then Hooke looks around, lowers his voice, and says that he has a proof that this inverse square law explains the elliptical orbits of Kepler. Well, Halley is impressed, but he's not sure he completely trusts Hooke. So, what does he do? Well, the next day he hops on the first stagecoach up to Cambridge University to visit his old buddy Isaac Newton, who's a professor there. So he says to Newton, "Hey, there's word on the street that the sun exerts an inverse square force that can explain the orbits of the planets." Hooke says he has a proof. And Newton says, "Yes, I've worked it all out." Well, Halley is a bit taken aback and says, "What? What did you find?" Newton says, "It is an ellipse." Now Halley is stunned. He says something like, "Gadzooks, how now, Newton?" Which in contemporary parlance basically means, "WTF, Newton? Why didn't you tell someone? Show me." So Newton starts rummaging through his desk drawers. "I've got the proof here somewhere," he says, but he can't seem to find it. Now, maybe Newton was so absent-minded that he could have misplaced one of the most important scientific discoveries of all time. But I suspect that he hadn't quite worked it all out on paper yet. On the other hand, he didn't want Hooke to get credit, so he was stalling for time, so he could later claim that he had discovered it before Hooke. It's also possible that Newton was in the process of figuring it out with calculus, his recent discovery. But there is a suspicion that Newton wanted to keep calculus a secret so he could use it later for other discoveries. In any case, he eventually, over the next couple of works, worked out this geometric proof of the elliptical orbits, and he sent his work to Halley. Over time, he continued to develop the ideas in greater detail, and this became his famous Principia.